Welcome back to the Lead channel. Today we're going to do a problem from the Energy Production Topic 8 unit, especially from 8.2, which is we got here an energy flow diagram, energy balance, energy flow diagram, looking at greenhouse gases and the energy balance between the Earth's atmosphere as well as the Earth's surface. So, without further ado, let's continue. This is an actual IB question. I will walk us through the parts. So, I will begin with question number 1. The intensity of the sun's radiation at the position of the Earth is approximately 1,400 watts per meter squared. Suggest why the average power received per unit of the Earth is 350 watts per meter squared. How to get from here to there? That's the question. So first, let's try to imagine what's happening here. Let's say you have the sun around here. Okay, we got the sun shining very bright. And as the radiation from the sun travels away towards the Earth, that power is spread over a sphere of influence. And the further away the radiation travels, the more dispersed, the more separated, the more diluted that power becomes. So by the time it comes to Earth, it's only a mere 1,400 watts per meter squared. So per meter in this sphere, I know it looks like a circle, that particular area will get only 1,400 watts of solar energy. If we take a close up here at the Earth's surface, and if you zoom in, you're pretty much only going to get, so only this part, this part, this part, all of that's going to get the radiation. So essentially it's only a circle's worth, only one side of the Earth is facing the sun will get the power. So that means we will have to take this 1,400 watts per meter squared, and to get the power here, we multiply this by the circle of the Earth, which in this case is pi r, being the radius of the Earth itself, squared. Okay, so this times pi r squared gives us the power that the Earth receives. But it needs to be received, we need to find the power received per unit area, which in this case is suggesting intensity. So we need to average this entire power over the entire surface area of the Earth. So that's a sphere. And the equation for the sphere is 4 pi r squared, and r being the radius of the Earth again. So this is averaging the power across the entire surface of the Earth. And if you noticed, the pi r squared cancels out, leaving us with 1,400 watts per meter squared divided by 4, which that pretty much gives us 350 watts per meter squared. Now, in this question, we have to be very, very careful. It says suggest why. It's not telling you to actually calculate. So please be careful of your command terms and read your question carefully. I've only showed you these steps just to show you how it works. But when you write it down in your IB on your IB exam, you do need to state and write out the reason. So first, the intensity, only the area of a circle, pi r squared, facing the sun will receive the sun's radiation. Therefore, multiplying the solar constant, in fact, that's what it is, by pi r squared. Then this power received must be averaged over the entire surface area of the Earth, which is 4 pi r squared. Okay, so if you take a look at the IB answer key, it pretty much talks about that, similar to effect. The first mark in this problem is you need to talk about how only the area of a circle that's facing the sun is going to receive that radiation. Thereby, you have to take the intensity at that point and multiply by the area to get the power. But then the power is an average throughout the entire surface area of the Earth itself. So that gives you the second point, 2 points to be said. Okay, so that's question 1A. Question 1B starts to look at the energy balance equation. The diagram shows a simplified model of the energy balance of the Earth's surface. The diagram shows radiation entering or leaving the Earth's surface only. And then if you take a look at the diagram, they tell you a few things like the atmospheric temperature, the radiation back to the atmosphere, radiation by the Earth's surface, transmitted through the atmosphere. The average equilibrium temperature of the Earth's surface is TE, and that of the atmosphere is TA equals to 242 kelvins. Using data from the diagram, state the emissivity of the atmosphere. So if you take a look at this diagram, the only way you can get the emissivity of the atmosphere is to look at the power that's radiated out of the atmosphere, and that's this term over here. And if you take a look at this guy, this looks pretty similar to Stefan Boltzmann's law, which states that power coming from a black body, radiated by a black body, is equivalent to the Stefan Boltzmann constant times emissivity times area times the temperature, and this for the atmosphere to the power of 4. We can also consider this as the power per unit of area by dividing both sides by area, giving us P, the power over area is our intensity, equals to Stefan Boltzmann constant times E times TA4. Now, take a look at the equivalency here. You have Stefan Boltzmann constant, TA to the power 4, which means 0.700 must be the emissivity of the atmosphere. So all you have to do is to state, which means you don't have to reason why. You just have to write down this value. And for the emissivity, it has no units, so no units are needed here. Moving on, only 1 mark. Number 2, show that the intensity of the radiation radiated by the atmosphere towards the Earth's surface is 136 watts per meter squared. We have to look at the radiation from the atmosphere. Going back, it should be 0.7 Stefan Boltzmann's constant times TA to the power 4. So we just need the intensity. So like I was saying before, the intensity we already found is Stefan Boltzmann times emissivity times the temperature of the atmosphere to the power of 4. If we put in everything, then Stefan Boltzmann constant is our 5.67 times 10 to the power of -8. This is pretty cool because look, it goes 5, 6, 7, 8. Even though it's in your data booklet, it's pretty cool to remember that value as well. Okay, so if I am not wrong, then the units of this one would be in watts per meters squared times kelvins to the power of 4. Since emissivity has no units and you're multiplying by the temperature, which is 242, I believe, 242 kelvins times, oh, I forgot the emissivity, times 242 kelvins and all that to the power 4, and I've forgotten the emissivity, 0.700, which is this. So emissivity basically means that whatever radiation is supposed to come out of the atmosphere, not all of it will. It's kind of that value, emissivity, is really talking about what that interface between your black body and the outside of your black body is, an interface. So it's kind of, if it's a less than 1, it means not everything will go through that interface, okay? And I mentioned this in class talking about if you have a perfect black body, it doesn't mean that all the radiation coming in must be all the radiation coming out. No, that's not what it is. A perfect black body means that interface is free of exchange of radiation between the inside and the outside of your black body. Okay, so just reiterating that. And now if we put it in our calculator, 5.67 times 10 to the power -8 times 0.7 times 242 to the power of 4, we get 136. 136 watts per meter squared. And Ivy likes you leaving that with only the exponents and not writing it over. Number 3, by reference to the energy balance of the Earth's surface, calculate the temperature of the Earth. So we have to do some energy balance here. So going back here, we have to look at basically what's coming in and coming out of the Earth's surface. Coming into the Earth's surface, we have the transmitted through the atmosphere, this one. We also have the radiation from the atmosphere. And the Earth is radiating something out, which is Stefan Boltzmann constant e to the power 4, suggesting that the Earth's surface is a perfect black body because we don't see emissivity here at all. So going and starting off with the energy balance, we assume that in this power in equals power out for energy flow. And as a result, we can also say that the intensity going in is also equal to intensity going out, assuming that the areas are equivalent, which it is in this case, because assuming you have all the atmosphere above the Earth's surface, or everywhere around the Earth's surface is the atmosphere, then you have area being relatively the same. So if we go back to our diagram, the intensity coming in is 245 watts per meter squared, as well as the radiation coming from the atmosphere. Now I'm going to choose not to use our previous value because it was rounded. So I'm going to do, coming in, we do know is 245 watts per meter squared, plus this one that's coming in over here, from the radiation from the atmosphere, sigma times, or actually I'll write 0.700 sigma Ta to the power 4, and this is equal to what's coming out of the Earth. We did assume it was a perfect black body, so Stefan Boltzmann constant, temperature of the Earth to the power of 4. Now we can solve for T(E), which is what we want. Let's divide both sides by the constant, and then taking everything to the root 4. After doing so, we get Te is equal to, going to our calculator, I have that value stored on my calculator, so I'm just going to add 245 to this. I'm going to divide by the Stefan Boltzmann constant, and then I am going to take everything to the power of 1 over 4, which is equivalent of saying taking the root of 4, which gives me 286 kelvins. Okay, next one. This is more written. Outline a mechanism by which part of the radiation radiated by the Earth's surface is absorbed by greenhouse gases in the atmosphere. So we need a mechanism, and we need which part of the radiation, and talking about greenhouse gases. So we do have to say what kind of radiation, which means knowing that the Earth re-radiates the power from the sun back in the form of infrared. So first we have to say something about infrared, and what's actually happening here is you have, maybe I'll draw it up here. So you have the radiation coming from the Earth going back up, and what's happening is that these particular molecules will vibrate with radiation of certain particular energies corresponding to the frequency of the EM wave, the electromagnetic wave. So in the infrared region, that translates to just enough energy to vibrate or get these greenhouse gases to oscillate, or whatever particular molecular energy level needed to get them to start to quote unquote wiggle. So then they start to wiggle back and forth, which means the radiation is now absorbed. The energy absorbed by the molecule, getting it to move around. Not move around as in translationally, but vibrationally, rotating, whatnot. And then certain times it will radiate that back out. So drop down in energy level, and that radiation comes back out, and it stops wiggling, quote unquote wiggle. How to put that into words? So notice that it's outlined. We're not going to go into detail, but it is 3 marks. So we want to talk about that this is infrared. So infrared radiation from the Earth's surface corresponding, or actually a better word is equivalent to exactly the same energy level, or actually to be more specific, the same molecular energy level needed to vibrate, oscillate, rotate these greenhouse gas molecules, which causes the infrared to be absorbed. So sometimes that last line, based on your reason, therefore, causes blah 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 to be absorbed, can give you that last mark. So the 1 mark talks about the infrared from the Earth's surface, and then one of the marks kind of talking about equivalent to the molecular energy level, which causes the molecules to vibrate, oscillate, jostle, wiggle, which is not a word you probably should use, but anyways, and as a result, the radiation gets absorbed. And that's a mechanism. I believe in your IB syllabus, it does talk about resonance, molecular resonance, which is another word if you would like to use instead of some of these, but also talk about vibrate. Vibrate is a really good one to use. Okay, so that will give you the 3 marks. Okay, next one, C2. Suggests why the incoming solar radiation is not affected by the mechanisms you outline in C1. So, because it is the exact, you need the exact equivalent, energy equivalent. If you look at if you take a look at the solar radiation is not infrared, is visible light. If we did not have a sun that emits visible radiation, our Earth would be pretty much dark, and that wouldn't be fun. So here, what you want to talk about is, you have to say it's not infrared, it is of the visible or UV range, which will not get absorbed by these greenhouse gases. They are incapable of absorbing them. Solar radiation is in the visible, or mostly because it's close to a black body, it does include other radiation as well, but it's mostly invisible / UV, visible UV spectrum, therefore cannot be absorbed by these molecules, requiring lower energy IR radiation to resonate or vibrate. But mostly you're going to get your mark from where you've talked about visible UV spectrum, and then saying therefore it cannot be absorbed by the molecules. Or you can say out as reason outlined above. Actually, if you add reason outline above. So even if you add these things, it kind of helps the examiner just to show your reasoning and whatnot. So I included the explanation below, but if you wrote reason outline as above, then they kind of have an idea. But more writing is always better than less writing, just to clarify for your sake. Okay, last one. Carbon dioxide is a greenhouse gas. State one source and one sink object that removes CO2 of this gas. So a source, you kind of have to be a little bit more specific. You can't just say industry or cars or whatnot. You kind of want to say, where does it actually come from? Where does a CO2, through what process do you get CO2? And in this case would be burning of fossil fuels. And then you can say in power plants or whatnot, or industries, power plants, or cars, etc. Okay, so this part you can change to something similar, but you definitely need the burning of fossil fuels, because that's it's more specific, and you definitely learn that in this unit. or in this, in 8, topic 8. Sink. So sink, this is a little bit more general because it's not as specific as covered compared to where it comes from. But anything that you can talk about, and you can talk about how you can just state oceans, especially big bodies of water that actually take up CO2. So that's oceans. You can say lakes, but another good one is trees. Trees is a good one. They do ultimately get absorbed by trees or used as for photosynthesis. So trees is a good one. The ocean's a good one. Dissolve back in water. These are the main ones that you definitely want to talk about. So it only says state 1. Okay, so there is a question regarding the energy balance. Notice that the math is not very difficult, but understanding where the math comes from is more so the case. So some places where there was a little bit more focus is understanding the energy balance, how to look at energy flow using power in equals power out. The other one is understanding a little bit about how the greenhouse gases work. How do they absorb energy from which part of the spectra, etc. And while you understand how that works, it actually does help you draw in your energy diagram as well. For example, modeling kind of how your solar radiation coming in doesn't get absorbed by the atmosphere. It actually goes straight to the Earth's surface because it's in the visible region. So that's one thing to kind of think about. But other than that, this is a pretty straightforward question. It's not, if you understand the material, it shouldn't be too difficult. So hopefully at least this video will give you a little bit of more explanation on each of these questions, and hopefully helps to maybe some degree. But anyways, thank you for watching, and let me know if you like another video regarding this kind of stuff or similar. Otherwise, see you next time on the Lee channel.